Hi, today we will continue the discussion of subtopic 11.2, Young's modulus. Let's continue the discussion.
Assalamualaikum and hi. Today we are going to learn about Young's modulus. Are you ready? Let's get started. Here is the learning outcome for Young's modulus. First, we are going to define Young's modulus. Next, we are going to discuss the strain energy from the force elongation graph. Next, we are going to discuss the strain energy per unit volume from the stress strain graph. Last but not least, we are going to solve the problems related to the Young's modulus. However, the problem solving will be discussed in the tutorial class. Young's modulus is also known as elastic modulus. It is denoted as Y. Young's modulus is defined as the ratio of the tensile stress to the tensile strain if the proportionality limit has not been exceeded. In the box is the equation for Young's modulus. Young's modulus is equal to tensile stress divided by tensile strain. From previous lesson, we know that stress equals to force divided by area and strain equals to elongation divided by the original length. When we arrange these two equations, we can get Young's modulus equals to force times the original length divided by area times elongation. The Young's modulus can be thought of as a stiffness of a material. In the other words, it is how easily it is bended or stretched. A material having a large elastic modulus or Young's modulus is very stiff and is difficult to deform. Young's modulus is a scalar quantity and the unit is kg per meter per second square or Newton per meter square or Pascal. Young's modulus depends on the type or nature of material. The value of Young's modulus is constant even if the length of wire is changed. The table below shows the value of Young's modulus for various types of material. The value for metals are much larger than those, for example, the nylon. The material with the greater value of Young's modulus undergoes the smaller change in length. Most solids have Young's moduli that are rather large, reflecting the fact that a large force is needed to change the length of a solid object. Now let's discuss about the relationship between the force constant K and Young's modulus Y for a wire. Just now we learned that Young's modulus is the ratio of stress to strain when the material deformation is completely elastic. As long as the proportionality limit is not exceeded, then the Hooke's law is obeyed. From the Hooke's law, we know that force equals to force constant K times elongation. And from the Young's modulus equation, we can get force equals to Young's modulus times area times elongation divided by the original length. Then we equate these two equations. Then we will get force constant times elongation equals to Young's modulus times area times elongations divided by the original length. After we cancel the elongation on both sides, then the equation will be force constant K equals to Young's modulus times area divided by the original length. Strain energy. Strain energy is defined as energy stored in a body due to deformation. Regarding force against extension graph, we need to consider a straight line from 0 until the proportionality limit only. At this stage, the wire or material will still return to its original length after the force is being released. The ability of wire or material to return to its original length is caused by energy stored called strain energy. Since the sample obeys Hooke's law and is below the elastic limit, The elastic strain energy can be calculated by calculating the area under graph. We also can use the equation for strain energy in the wire, that is half times force times elongation. Now we are going to discuss how to get strain energy per unit volume. From the statement of tensile stress and tensile strain, thus, the first equation is stress equals to force divided by area. We rearrange the equation, then we get force equals to stress times area. Next equation is strain. Strain equals to elongation divided by the original length. We rearrange the equation, then we get the elongation equals to strain times the original length. Then we substitute these two equations into the strain energy equation, that is half times force times elongation. Then we get half times stress times area times strain times the original length. Next, we rearrange again the equation to get strain energy equals to half times stress times strain times area times the original length. Remember, when the area multiply with the original length, then we can get volume. Finally, the equation for strain energy per unit volume is equal to half times stress times strain. Last but not least, let's refer to the stress against strain graph. We can calculate the strain energy per unit volume by calculating the area under stress strain graph, but remember, as long as the proportionality limit is not exceeded, then the Hooke's law is obeyed. We also can calculate the strain energy per unit volume by using the equation half times stress times strains.
That's all for now. Thank you.